Let's wait a couple more minutes for more people to show up. Okay, so let's get started. We'll continue from last time. So basically, last time we spent a lot of time talking about constraint optimization problems, right? So now often we're interested in solving a problem of following form. We're going to minimize over variables x some costs that depend on x, subject to, let's say, some equality constraint and inequality constraint in the variables. Right, so let me make sure I follow notation. So let's say I have a bunch of equality constraints, then some inequality constraints. Okay, so this is a fairly generic form of an optimization problem we're interested in. And the canonical problem you can think of as, let's say, minimizing generation cost subject to a power balance constraint and the inequality constraints on the generation upper and lower bounds. So these kind of problems are in general very hard to solve. Okay, so most of the problems of this form, there's no guarantee you can solve them. But in this class, we're going to look at a special form of the problem where we can solve. We're going to look at a special form. And then the idea is basically to extend the picture of a unconstrained optimization to the picture of constrained optimization. Okay, so, right, so like let's look at a very simple, let's say, unconstrained optimization problem. Okay, let's say we're going to minimize over x, let's say something like x minus 2 squared. Okay. So this is a unconstrained optimization, right? This is unconstrained optimization. This is a so the way you solve it is basically you're going to take a derivative with respect to x. You get this 2x minus 2, set this equal to 0, and you can claim x star equals to 2. So the minimizer of this unconstrained optimization is given by when the derivative is 0. Okay. So this is from sort of simple calculus, we know this. But to extend this to a constraint optimization problem, it's better to have a geometric picture of this. Okay, so this is a algebraic procedure, meaning taking derivative, set to 0, solve the equation. Okay. In a constraint optimization, we also want a procedure, an algebraic, basically a sort of procedure to work. But then to get the procedure, it'd be better to have a picture in mind of why does this work. Okay? So if you look at this function, what does this function look like? Right? So this is x, this is x minus 2 squared. So it's centered at 2. Okay, so it's some quadratic like this, So then geometrically, why does the gradient being 0, the derivative being 0, correspond to the minimizer of the function? Right. So the question is, how do I link the algebraic procedure to the geometry of the problem? Okay. So if you look at the gradient of the function, okay, if you look at the gradient of function, let's say I'm computing the gradient at this point. Okay. Let's say I'm computing the gradient at this point. The gradient basically points upwards, right? So this is where the gradient points. This is the ddx, x minus 2 squared. Okay. This gradient points upwards. Okay. So from our algebra, it tells us if the gradient is not 0, it cannot be a minimizer, right? It cannot be a local optimal point. Okay. So geometrically, why is this the case? Right? So if I give you a function, I tell you at this point, the gradient is not 0 and it points, in some direction. Why does it imply that this point cannot be a minimizer? Why does this point imply that this point cannot be an optimality, cannot be an optimal solution?
Because a non-zero gradient means that there's a lower point.
Right. So the non-zero gradient means there is some direction you can go to decrease the function value, right? The gradient, remember, is the direction of when the function value increases. But that implies if you go reverse of the gradient, the function value will decrease, right? So this decreases the function value. Okay, this decreases the function value. So since it decreases the function value, that point cannot be minimized. Right? I can move in the opposite direction to get a better solution. Okay, so geometrically, this is why it's sort of it's a necessary condition for the gradient to be 0. So it's a similar thing here. If you look at this point, the gradient points that way. So there's a better, so this is a sort of, or you can call this a descent direction. Okay, right, there's somewhere I can go to reduce the function value, right? There's some point I can go to reduce the function value. So a point with non-zero gradient cannot be optimal, cannot be a minimizer. Right, so similarly, we can consider a two-dimensional problem, and the same intuition carries over, right? So last time we looked at, if you look at this optimization problem, if you draw the level sets of the function, these are ellipses, right? So let's say this is some level set, some level set of the function where the functional value is constant. If you look at the gradient, right? If you look at the gradient of the function, what the gradient are basically, pointing out, right? Pointing in this type of directions. So if they're not 0, that means you have a decent direction you can go, right? So so this means that to get a minimum, we follow the gradient. When the gradient tells you there's a direction you can go, you can keep going that direction. When the gradient is 0, or geometrically tells you there's nowhere to go, you can, at least that point has a possibility of being a minimum. Okay. So this is for unconstrained optimization, why we have the first order condition that the derivative or the gradient is 0. So now we're going to look at the constraint optimization problem, right? So let's look at constraint optimization and what happens. In constraint optimization, the idea is actually the same. We're going to follow the gradient until we cannot go somewhere. Okay? Until we cannot go somewhere. All right, so let's look at constraint optimization. Okay. So let's say our problem is the following. Okay, the following. We're going to solve this optimization problem subject to a sum constraint. Right? We're going to solve it subject to the constraint that the sum of x1, x2 equals to 5. Okay? We're going to solve subject to this constraint. So for this constraint, 5 equals to x1 plus x2. Geometrically, what is it? This kind of constraint, geometrically, what does it represent? It's kind of equality constraint. So this is not a trick question, right? So what is x1 plus x2 equals to 5? Right, so this is a line, right? So all this is a line. Right? This is a line in space, right? So x1 plus x2 equals to a constant, there's some line in space, okay? So here the green and the orange line are the level sets of the function again, right? Are the level sets of the function, okay? So for this line in space, let's say it touches the green function here, and the line goes something like this. Okay, so this is my line. This is 5 minus x1 equals x2 equals 0. Okay, right, so this is my equality constraint. So all the solutions must stay on this line. Okay, so all the solutions has to be in this line, has to be on this line, right? So you move a solution, all the solution can do is basically, go up and down the line. Okay, right? This is the equality constraint. So all our solutions must satisfy, must lie on this line. So what we're looking at is basically, we're going to slide points along this line until I cannot make the solution smaller. Okay, so this is our goal. I'm going to slide all these points along this line, trying to see if I can make these objective values smaller or not. Okay. All right, so this is our goal, right? So this is different than unconstrained optimization, because now we're constrained, right, to move along this line. Okay, we're constrained to move along this line. So let's see, when should we stop moving along this line? Okay, so if you look at the gradient, oops, what happened to my pictures? Right, so if you look at point on this line, okay, so let's look at the gradient of the function along this line. Okay, so let's look at some of the gradient of the function. So this gradient of the function here, so as a reminder, f is 0.25 x1 squared plus x2 squared. So this gradient is 0.5 x1, x2, to x2. Okay, so this is our gradient of the function. So this gradient points in many directions, right? So here, let's say it points something like this. Here it points something like this. And here it points sort of perpendicular, something like this. Okay, so this is our gradient at the multiple points of the line, right? So now let's ask a question. Right, so this is the red point is a feasible point, right? It satisfies the equality constraints, satisfy equality constraint. Another question we can ask is, can this point be the optimal point? Does it minimize f? Does it can minimize the function value? Right, so let's say I come along and I tell you this red point is the optimal point, right? Can it happen? Can this point be optimal? So why is it not minimized? It does satisfy equality constraint, but how can we conclude this actually is not the best point? So which way can I go to decrease the function value? Why is this point no good? So right, so the chance is, there's a better point if you just look at the function evaluation. But let's say I don't know this, right? Let's say I don't know this. Let's say I'm simply given the geometry of this, and I tell you and I claim, this is a point. But geometrically, is there a descent direction? right? So our question is, can I descend in this direction? Right? Can I do a descending direction? So if you look at, so if you pretend the problem is unconstrained, if you pretend the problem is unconstrained, what happens? You should go in this direction, right? If the problem is unconstrained, you'll go in the blue direction. Since the problem is constrained, you cannot leave the black line. You cannot leave the equality line. But which direction would you want to go? Right? If you cannot leave the black line, you will still go in this direction, right? So this is a descent direction. Okay, this is still descent direction. Because if I cannot go exactly opposite to the gradient, that's okay. Right? If I cannot go directly opposite to the gradient, I can try to go as opposite as possible. Okay? I can try to go as opposite as possible. Okay? So this is the point. As even though I cannot go completely 180 degrees, there's still some descent direction for me to go. Right? There's some still descent direction for me to go in this point. Okay? So does this make sense? Right? I'm at this red point, I want to go opposite direction, I can't. Right? So, but because there's some still direction for me to reduce function value. So this is the important point optimization. The important point optimization is you may have heard, follow the gradient or go in the opposite direction of the gradient to optimize the problem. That's not necessary. All you do is if you want to minimize the problem, is don't go in the direction that's 90 degrees to the, right, within 90 degrees to the gradient. Okay, so a finer point optimization is following. So let's insert a page, talk about this point. Right? So a finer point is this in optimization, and this is really good to know. As if I have a gradient this way, right? So then I have a minus this gradient in this point. What happens is I can divide the space like this, Okay, so any direction here will increase the value of f. Will make f larger, right? You don't have to go exactly along the gradient. As long as you're within 90 degrees of the gradient, you increase it. Similarly, any vector that's more than 90 degrees away, this will decrease the value of f. Okay, this will decrease the value of f. Right. So this is the geometric picture of which direction you're going. Right. So as long as you're aligned with the gradient, you increase the value. If you're anti-aligned with the gradient, you decrease the value. So you come back to this picture is I don't have to go, exactly against the gradient. As long as this angle is less than 90 degrees, I'm still decreasing the functional value. Okay? That's what I want, right? I only stop when the angle is 90 degrees. Okay, so that's the entirety of constraint optimization. It's basically this. It's recognizing that for unconstrained optimization, you just go against a gradient. Here, you go against a gradient as much as you can. Okay? As much as you can, following the constraint. Right? So this is all you want to do. So similarly, right? So similarly for this point, it's basically if you come here, we still have a descent direction. This is the descent direction. Right, so this is still a descent direction. meaning that you're reducing the function value. Okay, you're reducing the function value. So when do you stop? Well, you only stop if you come to this point, right? Because at this point, your gradient is completely orthogonal to the constraint. Okay, so this point, the gradient is completely orthogonal to the constraint. So anti-gradient is pointing this way, but there's nowhere to go, right? There's nowhere to go. You want to move opposite to the gradient. But to move opposite to the gradient, you have to move off the constraint. You have to move off the constraint. But that doesn't make sense because you have to be on satisfy the constraint to be feasible. And then this is the point you stop. This is the point you stop, all right? So the geometric picture changes from the gradient 0. It changes to the fact that the gradient should be perpendicular to the constraint. Because if the gradient is perpendicular to the constraint, the only thing you can do to change the value of the function or reduce the value of the function is to move off the constraint. That's not possible, so that's when you stop, right? So there's sort of geometric picture. As you look for this kind of perpendicular things to happen, right? You test for this kind of, you test for when two vectors, right? You test for, as a constraint, basically perpendicular to the gradient. If it is, then you stop. Any question with this geometric picture? Any question with the geometry? So we'll translate this into algebraic condition that we can check. But for now, any question with the geometry? So this is important. So knowing this there's an easy recipe to remember to do constraint optimization. But it's good to have this kind of picture in mind. It will serve you well. It will serve you well for any other type of problems, right? So the one thing to always remember is basically you really understand the problem when you can draw a picture. Right? So you always want to be able to explain things to people in pictures. So this is the picture explanation of constraint optimization of the searching procedure. Then we're going to try to turn it into an algebraic procedure. Okay, how do we do this with just numbers, right? So the algebraic procedure comes down to this. How do you tell when the gradient is perpendicular to your constraint, right? The idea is, how do I tell this, right? This is, orthogonality or, things being perpendicular to each other is a geometric notion, right? But a computer doesn't know this, right? So how do we do this in algebra? Well, the way to do it is the following way. So if you have, right? So basically, if you look at the constraint, if you look at the constraint, right? So as a reminder, our constraint is omega equals to 5 minus 1 minus 2 equals to 0. Okay. So I can similarly take a gradient of this line. Yeah, I can take a gradient of this line. This is minus 1 minus 1. Right? This is my gradient of the line. What this is a normal vector to the constraint. Okay, this is a normal vector. Right? So basically it says if you have a line, the perpendicular vector to you is given by the gradient of the line. Right? This is similarly as, you can think of this as slope. Right? This is the description of the line as as the normal vector. Right? This is the normal vector to a hyperplane or to a line. Right? So this is very easy to check. So every point on the line is perpendicular to this vector. Okay? Every direction on the line. So now this gives us an easy way to tell whether my gradient is perpendicular to this or not. Okay? This is actually an easy way to tell what happens to my gradient, because my picture becomes this, right? My picture becomes that at every point, I have a gradient of the function. I have a gradient of the function. I have a gradient of the function. I have a gradient of the constraint. So I want to know when they're perpendicular to each other. Okay, so I want to know when this gradient is perpendicular to the constraint. Okay? So our goal is to find grad of f such that the gradient is perpendicular, is orthogonal to this constraint. Okay? We want to do this, but we always know this is orthogonal to my constraint, right? So we want to find a vector that's perpendicular to it. We know the gradient of the constraint itself is orthogonal to it. So this together implies we want this to be in the, right? So we want this basically to be so how do we say this? We want this to be, these two to be, on the same aligned or anti-aligned So we want this to be in the same line, basically, right? We're looking for a vector that satisfy the same condition. So we have a constraint. We're looking for two vectors that's both perpendicular or actually orthogonal to the constraint. Okay, so this is our goal. We're looking for this type of vectors. Okay, so basically we want this to be parallel. Okay, we want these two vectors to be parallel. They're both orthogonal to the constraint. Okay, so this is what we want, right? So how do we get them to be parallel to each other then? Right, so we want this to be parallel. So if you look at the picture as, we want them to be parallel to each other. We want them to be parallel to each other in the same direction. Okay? And this to be parallel. So mathematically, how do we determine this? How do you check if two vectors are parallel to each other? Okay, how do I check? So I give you basically, our condition is find x such that this gradient of x and gradient omega are parallel. But how do we check this? Right? How do we check two things are parallel to each other? So finding the angles between dot product is too hard. I have to take a dot product. I don't know what these angles are. A dot product includes multiplying things. I don't want to multiply things. I don't want to multiply two vectors. Can I do this without multiplying two vectors?
Can you just like check for linear dependence or?
Right, so we want to check for linear dependence, right? The goal is to check for linear dependence. So two vectors are parallel or exactly perfectly linear dependent if there exists. So this parallel is equivalent to if there exists a lambda, if this is a lambda, such that this plus lambda equal to 0, right? They're on the same line if one is a scaled version of the other. Right? This means they're linearly dependent, right? The two vectors are linearly dependent to each other, meaning there exists a number such that one is a scaling of the other. Okay? There exists a real number lambda such that this equality holds. Right? This is basically our goal. Okay? So now our condition becomes the following, right? So we want to say, so our goal is now the following, right? So find lambda such that this is true. Or in coordinates, if you write it out for this two-dimensional problem as we want this to happen for the first coordinate. We want this to happen. This is the partial derivative. For the second coordinate, and I have an equality constraint, so I better have this thing. Right, so this is, my constraint is always here, right? So I have three equations to solve, okay? So basically, if I can find the lambda and x satisfy all the three equations at the same time, then potentially I have a minimizer. Okay, then potentially I have a minimizer, right? The lambda exists tells me the two vectors are parallel to each other. Okay, my gradient is basically orthogonal to the constraint. And then of course I need to always satisfy the constraint itself. So together I have three variables. All right. So any question with this at this point? All right, so if I can find such a lambda and x's satisfying these conditions, then we're done, right? Then we're okay. Right? So the question is, can I find the lambda? Okay, can I find? The question is, why this easier, right? Why this easier than before? Okay, how? Did I really remove the constraint optimization problem? Okay, did I really remove this? Okay, so let's take a look. But before that, right? So this is typed out version. The important thing to remember is lambda is called a Lagrange multiplier. Okay, this lambda has its own special name, and it's called a Lagrange multiplier. Okay. And the word multiplier comes from the fact that it's multiplying a vector. Okay, so Lagrange is from the guy who discovered this. Multiplier says this is a multiplication between this number and the derivative. Okay, and the goal is, can I search for this? So if you look at this, right? If you look at these three constraints, your question is, okay, why is this a easier problem than before? Right? Before I had one equality constraint. Now I have more equations to solve. So how is this easier? Well, this is an easier problem because you can actually summarize all these different constraints. Okay, we can summarize all the different constraints. And once you summarize this way, and suddenly this becomes a easier problem. Right, this is an easier problem because I can define the following function. Okay? So let me define the Lagrangian. This is called the Lagrangian. x1, x2, and lambda. Okay? I can define this Lagrangian of x1, x2, plus lambda of omega to x1, x2. Okay? So let's define this function. Okay? Let's just simply define this function now. And then for our function, what we have is, so what happens if we optimize over x1, x2, and lambda at the same time? So if we look at the original function, it's only depending on x1, x2 with the equality constraint. So now I'm going to remove the equality constraint. I'm going to put it upstairs in the objective function, right? So this was our old equality constraint. So we're going to remove the equality constraint, put it up in the objective function, basically. And we're going to now treat this as an unconstrained problem. Okay, so now this is now unconstrained. Okay, this problem is now unconstrained, right? So for this unconstrained problem, now it's easy to solve. we'll just take the partial derivative with respect to every variable and set it to 0. Okay. Right? So if you look at this, then what is a derivative with respect to x1? This is df dx1 plus lambda of the constraint equal to 0. Similarly, for x2, this is df dx2 equal to 0. And if you take this with respect to lambda, we just get omega x1, x2 equals to 0. Okay. Right? So I treat this as an unconstrained problem. I get back the same. I get back the same bunch of equations. Okay. So this and this, they are the same. They're the same set of equations as before. They're the same set of equations as before. So what I did is actually I converted an equality constraint problem to an unconstrained problem. Okay, this problem now has no constraints. But if you construct the problem this way, it turns out the solution to this unconstrained Lagrangian, when you minimize the Lagrangian, is the same as a solution when you solve the equality constraint problem. Okay, so this is basically the entire point of defining Lagrange multiplier. As you do this multiplier, then this is actually a conversion of a constraint optimization to an unconstrained optimization problem. Okay, this is basically how we solve the problems this way. As we're gonna basically reflect, remove the constraint upstairs and solve the problem this way. Okay. So let's do an example. Let's do an example to see why this makes our life easier. Let's do an example to see why this makes our life easier. So this is just a summary of the problem. Okay. Now here, we're going to look at an equation basically of this form, right? Minimize this, subject to this cost function, subject to this constraint. So our first step is to write down the Lagrangian. Okay, we're going to write down the Lagrangian. This depends on 3 variables now, x1, x2, and lambda. Okay, this depends on 3 variables. Okay, so let's take a derivative. Let's take a derivative. x1. This is 0.5 x1 minus lambda equals 0. This is 2x2 minus lambda equals 0, right? So I'm taking partial derivatives of the Lagrangian with respect to x1, x2, and lambda. This is, I recover 5 minus x2 equals to 0. Okay? I simply recover this equation. But now we get a system of linear equations, right? So now I'm looking for x1, x2, lambda that solves all 3 equations together. So this is a particularly simple system of equations to solve, right? So if we can set up this system, for example, all we're solving is x1, x2, lambda, 0.5, 0, minus 1, 0, 2, minus 1, minus 1, minus 1, equal to this way, 1, 1 equals to 0, 0, 5. Okay, is this clear, right? So I can convert this to a matrix form. Then you can do whatever you do to solve this matrix equation. Okay? This is not a very difficult equation to solve. Okay? You can either solve this by hand, using a computer, or use substitutions. However you want to solve this, you can go for it. This gives us x1 equals to 2. Sorry, x1 not equal to 2. x1 equal to 4, x2 equals to 1, and lambda equals to 2. Okay? And lambda equals 2. So this is the optimal solution. Okay, this is the optimal solution. Right? So if we want to solve this way, we did not have to do any substitution, right? We did not have to solve any quadratic. We did not have to, deal with squares, things like this. Is all we do we set up the Lagrangian, differentiate away, get a linear system of equations, and solve them this way. Okay, and solve them this way. So any questions with this procedure?
Professor?
Yeah.
Can I see the matrix you just made?
Oh, sure, yeah.
For the matrix, the third row, like the 1, 1, I think that's 0.
There. Yeah.
But I mean, for this one, the from the delta L divided by a delta lambda.
Yeah.
Which is a 5 minus x1 minus x2. Remove the x1, x2. Okay, thank you.
Yeah, x1 plus x2 equals 5, right?
So remove the 5 equals to like x1 plus x2 equal to the 5.
Yeah. This is
Can I do
third
that?
row.
Okay. Sure. Thank you.
Okay, any other questions with this procedure? So basically, when you do a homework or do the final exam, this is the procedure you follow. And this procedure is actually quite easy to do. The Lagrangian is a well-defined function, right? You just set up this way. For all our problems, it will be all quadratic, basically. You just differentiate, you get a bunch of system of linear equations, and just solve the system of linear equations. Right? And the reason of why this works, is basically the geometry we set. Okay, so if you look at Lagrangian without knowing the picture, it looks a little bit, somewhat mysterious, right? Why is it, why should I just multiply this by lambda and start taking derivatives? Basically, lambda encodes the fact that two vectors are parallel to each other. Okay, that's what all lambda is doing. It's encoding this condition. Then the rest is just through calculus. Any questions with this? Okay, so if not, then let's break here. We'll have to, say much more about lambda, the economic interpretation of lambda, and all this following that. So let's come back at 10:23. Okay, we'll resume the lecture at 10:23. Have any question about homework, you can ask now. Right? I got several emails about homework. So if you still have questions, please ask now.
Hi, Professor.
Yeah.
I have a question for the homework 1. So I got all the data from the data sheet, and
Right.
also I just built the admittance matrix Y.
Right.
So what I want to do, like the question is also asking about the initialize of data. What do you mean by initialize?
So when you solve the Newton-Raphson, right, you have to initialize the algorithm at some point, right?
Like.
Right. So so Newton-Raphson, remember, you have x0, right? You have to start the algorithm at some point. So we are.
So which means like I make the assumption like at some point like the wave. I already know the V1, right?
Right. So V1, right? So all the V's right? So for the PV bus, the V. But for some other buses, you don't know the voltage, right? You have to guess. Basically, to run the algorithm, you basically need a guess, right? You need a guess at the first point.
Okay. So should I guess like initialize the? I know the V1 and but what I don't know is what I don't know.
Right. So you don't know, right? So at some point you don't know, right? So let's say you have a PQ bus. You don't know the V, you don't know the theta, right?
Yes.
But for the Newton-Raphson algorithm to work, you have to give it an initial guess.
So
right? So you have to give initial guess, right? Without that initial guess, this algorithm cannot run, right? So what initial guess do you use, right? So get initial guess is to guess V equals to 1 and the angle is 0. So that's called a flat start.
From this data, I know the V set, which means which means I know all the voltage at the bus, right?
No, for a PQ bus, you don't know the V.
But what's V set?
V set is, you can ignore that for now, actually. We'll use that later. Yeah.
So which means I only know the V1 selects a 1 and angle is 0.
So, right, so we have three types of buses, right? We have a slack bus. So you know for that bus, V is 1 and angle is 0.
Okay, so which means
For the
get,
PV bus, you know the V, right? You know the V and the P. You don't know Q. You don't know the angle. Then for the PQ bus, you don't know V, you don't know angle.
so like for the D is for the PQ bus. The type
So
D.
if you look at the data sheet, right, there's three types of buses, right?
Yes,
So S is slack bus,
slack bus.
right? So that one we know V and theta, right?
Yes.
Okay, so then if you look at the,
D.
let's say if you look at bus 2, right? Bus 2 is a generator bus, right?
Yeah.
Bus 2 is a generator bus. Sorry, yeah, so bus 2 is a generator bus. And for that one, you can take, you know, the P to be the P megawatt given, and you can take the V to be V set actually for that value. For that value, you can take V to be V set.
Okay, V set.
Yeah. So theta you don't know.
Theta.
Right. For demand, you PQ are given, right? The P megawatt, Q megawatt. And the
Yes.
V you don't know, the theta you don't know.
But for the angle theta, since I know the P and the Q, I can calculate the angle for at this point.
How do you calculate the angle without running the right? So the point of running the Newton-Raphson is to compute the angle. But if you don't run the Newton-Raphson, how do you compute the angle?
Okay, I was thinking like maybe I know the P and the Q, I know the power, like the power factor, and get an angle.
How do you compute the angle if you know the P and Q? Right. So that the whole point is to compute the angle. That's correct. But so you need to solve a nonlinear equation, right? You need to solve a system of nonlinear equations to compute the angle.
So which means I do the initialize the theta from the bus 1 to the bus 12.
Right. You need to get some data.
Okay, and also like the voltage bus is also like the V1 to the V12, but I know the V1 is 1.
No. So there's two kinds of buses. There's three kinds of buses, right? There's a slack. There's
Okay.
PV bus or PQ bus, right?
And also the generator bus is also the voltage bus there.
Yeah. So generator is a PV bus.
The generator, I know the V set is just the voltage bus.
Yeah. You know V set, right? So there you know V set. So you can hard code that in, right? So that you can, you know, you don't need to solve for V anymore, but you still need to solve for theta.
And how about another question is how do I build the function? Because I know the P equals the Vk times Vi, like sometimes
Yeah.
some of the
Right.
G times the cosine theta. But that seems a lot of work.
Like a lot of work coding it, or?
No, because like the P1 equals to the P1 times the G times the cosine plus the
Right.
B times sine theta.
Yeah.
Plus the P1 times P2 and until to the P1 times V1 times V12. That's right?
So are you saying it's a lot of work coding it, or?
I mean, is that the right formula? Cause like so.
Yeah, it's a formula, right?
So I starting to like say from the V1 times V1 until to the V1 times the V12 to get the.
Sure, yeah, sure. That's a formula. But you're not going to type out the entire formula, right? You basically have a vector of V, vector of angle, vector of P, vector of Q. And you're going to do a loop, right, throughout this.
Oh yeah, yes, I'm going to do.
Yeah, so it's actually coding it is not that long. It's a few lines.
How about do the derivative, gets the Jacobian matrix?
Right, so for the Jacobian matrix, for each component, there's a well-defined formula, right? I think we actually did that formula in class, right?
Did we? Oh,
Yeah.
I know the Jacobian like it's just a full part.
Right, but for each component of the Jacobian, we had a formula, right? Did we not have a formula?
What do you mean by the formula?
So
yeah, we do have a formula. It was given.
Yeah, so we have a formula in class, right? Just copy the formula, just loop through that formula basically. It's still sort of a loop you can write. Do we not? So let me check the notes. I forgot exactly which class, but I thought there was a formula.
Okay. I don't remember the Jacobian had a formula here.
Yeah, we have formulas for each quarter of the Jacobian, and then you just concatenate those together to get the full Jacobian.
You mean the, okay.
Like J1, J2,
Yeah.
J3.
Oh,
J4.
J11, J12, J21, J22.
Yeah, exactly.
Yeah.
Oh, for here we got the J11 just equal to the minus BIG.
Yeah. So there's, is it not?
And
Basically, you can, for each of the component, you can take a partial derivative, right? You can write out what that formula is. Then you just loop through to construct the matrix, the Jacobian matrix.
Well, that would be good to use the formula, because if I do the derivative for everything, that would be always some small error.
No, the point is to be able to do this derivative, right? So this homework, the point is to basically debug the error. So I'm not assuming that, most of you will get this to be perfect, right? So the grading is actually very little depending on getting the answer exactly right. As you're handing a code, has to run, for example. First of all, it has to run. So your code has to run without bugs.
Okay.
Then you have to document the code and show what you're doing. Now, whether you get the exactly correct or not is very little actually to do with how many points you get for that question. Because after this week, the Trisha will give you her code. And we'll start from that one, but we'll keep modifying it.
Okay. So for that formula, like the Jacobian formula, like the four part J11, J12, J21, J22, and I can directly use the formula like the J12 and the J21 also all 0.
I'm not sure we're looking at the right formula. This may be better offline, taken offline, the two of us look at it. I'm not sure which one, but there is a power flow equation, right? And you just take partial derivatives. It's not very complicated to take that partial derivative, right? I mean, some sine, some cosine, just go ahead and take derivatives with that.
Hey, Professor.
Yeah.
For building the Jacobian, I know we usually are supposed to not include the voltages and angles that are set like on the PQ buses, I guess it is. But I'm a little confused on there's some buses like 2, 3, whatever they are, and they're not like in a straight line or at the beginning. So I'm not sure. Are we just supposed to skip those?
So
those in the Jacobian, or do we just set them as values?
Oh, so those are 0, right? So if there's not connected, then they're just 0.
No, I don't mean the connections. Like the admittance, multiplying by the admittance matrix is going to get rid of those.
Yeah.
But as far as we have the solution,
I see. So you're talking about, let's say you have a PV bus, and what happens to it, right? Are you talking about that?
Yeah, I guess.
Okay, yeah.
So for the set values.
Right, okay. So let's go over that. So let's see where we are. So, all right, so I think we were saying let's say I have a PQ bus, right? So let's do the PQ bus first. For a PQ bus, then, I have something like, I have all of these, right? So this is all I have. This is all I have for the PQ bus. But let's say for a PV bus, right? So your question is, do do I have this value, right? Right? Your question is basically
well,
this.
we have the V set that you've given
We have
us.
the
for
V
that,
set, right?
so
Yeah,
we
we have
don't
V
have to
set.
we don't have to solve for it, but
Right, we don't have to solve for it. So we
but we
actually
need to include it in like our solution matrix. If we don't exclude that bus as a variable, like the variables of that bus, it's going to end up in our solution from the Jacobian matrix. So
right.
do we just not include the solutions given when we modify the values for the next iteration?
Right. So for this, so the way to do this is to look at the number of variables we have. So let's look at this. Let's look at this example. Let's do it. Yeah. So that's a good question. So let's say this is slack, right? So let's say this is slack. Let's say this is PV. This is PQ, right? So let's say this is bus 1, bus 2, bus 3. So let's look at how many variables we have for this one, right? So we have theta 2 as a variable, V3 is a variable, theta 3 is a variable, right? Okay, so then our equation becomes the following, right? So we have, so these are the variables. Then our equations are P2 equals to, some things, right? P3 equals to some things, Q3 equals to a bunch of things. Okay? So our Jacobian for this case is, we have dP2, d theta 2, right? This always is there. This is always there. We have dP2, d theta 3, dP2, dV3. Okay, so this is our one row of our Jacobian. Right, so since V2 is given, this is a PV bus, so V2 is some set number. We don't need to solve it anymore. We can directly hard code that into the equation, right? So it's a constant now for us. So this is one row for it. Then our Jacobian is dP3, d theta 2, dP3, d theta 3, dP3, dV3. Okay, and dQ3, d theta 2, dQ3, d theta 3, dQ3, dV3. Right, so this is our Jacobian now for this small example. Right, so slack, since we know both voltage and angle, they're not variables, they don't enter this. For the PV bus, only the theta is a variable. So we basically basically V2 is not a variable anymore, it's just some number. We can put that number directly into the equation. So that we don't need to take a derivative with respect to V2 anymore. Then we end up with three equations, P2, P3, Q3. So our Jacobian is a 3x3 matrix.
Okay, yeah, that is helpful.
Yeah.
Is there any way to just somehow like include the set values in the equations and then still like, because I'm not sure if you can like I'm not sure the dimensions of the Jacobian
The dimension will work out. The
can...
dimension will work out. The dimension always work out for this problem.
Okay.
Always work out, because if you have a PV bus, you basically reduce the variable size by 1 because V is not a variable anymore. But Q is not an equation anymore, so you reduce the number of equation by 1. So you always get a square matrix for the Jacobian. So the number of variables and number of equations always lines up. Because anytime you knock down the size of variable by 1, then the equation also goes down by 1.
Okay, gotcha.
Yeah, so that you always end up with this sort of square matrix. This is the size always works out.
So it's not feasible to get a Jacobian if you include set values in there?
You can get a Jacobian if you can include the set value, but then you have basically work with that as an equality constraint, right? And becomes tricky when that is an equality constraint for you. So the easiest thing to do in this case is just to think of that as a given number and get a smaller number of equations.
Okay, because what I was trying to do is include all the set values, and then it was just becoming kind of a mess.
Yeah. So set values, you can just hard code them in and to reduce the size of the Jacobian. So for our test system, No, Jacobian is not 24 by 24, right? So it's not some smaller size matrix.
Okay, thank you.
Yeah, thanks. Yeah. So any other question about homework? Yeah. So I got several emails. So please ask questions. It's not easy to get a power flow equation working. It's not easy. So if you can get if you really can get it working, don't just try your best. Try at least to document your code. Make everything make sense. You will get vast majority of the points from that equation because we'll be doing a lot of things to this system. So if your code works, it's great. If it doesn't work, Trisha will post a standardized version of the code. Well, if you can't get your own code to work, you can work with that one. But this is where you should try to make it work.
Actually, another quick question. So,
yeah, go ahead.
We know the injected active and reactive power, it's columns B and C in the bus data sheet. And so my question is, you said we'd have to change the sign or accommodate the sign depending on whether it's a demand or a generation bus, correct?
Yes, yes.
I guess my question is, in class, the one that we did, if I'm not mistaken, it was a slack and a demand bus. And my intuition was that if it's a demand bus, we'd put the injected as a negative, the P injected as negative, and the Q injected.
Yes, yes.
But the thing is, for the problem that we did in class, we never actually did that. We subtracted the P injected and the Q injected for the power flow equations, and we never did flip the signs for its on lecture 10. I should probably ask this after class.
Right. So yeah, I think I get what you mean. So in the class, basically, we need the sign to be correct to calculate the mismatch, right? So when you look at the Jacobian, the sign actually of the demand or generation, the PQ set numbers doesn't enter this into this Jacobian, right? Those are constants, right? P inject, Q inject is the constant product of the equality, basically, of the equations. But when you take the partial derivatives, actually they don't enter into the Jacobian. Does this make sense?
Yeah, that makes sense. But then,
so you can do the Newton-Raphson update with the Jacobian and the current function evaluation, things like this. The thing you need to make sure is you need to check the mismatch, right? So when you check the mismatch, you need to be able to look at the sign of the function. Right, so we check the mismatch, right? So you basically get some v and theta, you plug into the power flow equation. And then some values for p will be positive, some values for p will be negative, right? So then when you subtract, when you check the mismatch of those values with the, let's say the generator or the load bus, the p on the generator or the load bus, you need to be able to subtract the weights or the correct value to check the mismatch. So those are. So.
Okay, I think that makes sense.
Yeah, so you need basically, there's supposed to be two signs, right, for generator and load, right? So if your code is always subtracting, always adding, there may be an error because the mismatch, may be small, but because of sign error, right? You're treating a generator as a load because you're also subtracting it. That will create an error, and you wouldn't terminate when you're supposed to. Right? So that's when you check for the mismatch, you need to be aware what the correct sign should be, in the convention.
Could you just tell me quickly what is F max on the spreadsheet?
Oh, F max is the maximum line flow value.
Okay.
Which we'll be using later. So next homework, we'll be looking at F max. Basically, right? So if you look at spreadsheet, there are some numbers that's 9999, so that means unlimited, essentially, code as. Right? There are some years 95, 100, so those are limits. So later down the line, what we will be playing with this, test system is, I would say, is the line flow satisfied? And I can ask, suppose I change the line flow limit from bus 2 to bus 4 from 9999 to 50. Is it still satisfied? So these are the questions we'll ask.
Okay, thank you.
Yeah. Yeah, so you want to try. So for the point for this homework, you want to try. Because, even if you get, somebody else's code, and if you're not too familiar with this system, you may not be able to use the other code correctly. Right? So we'll have a standardized code if that's one that we can get your own homework to work, your own code to work. But it'd be good to go through all this, try to work through this on your own, or at least once. Right, and really, if you go work for a large utility or you go work for a system operator, large part of your life will be solving this type of equations. You go to a vendor, for example, you go work for GE, who sells software to utilities and operators. 100% of your life sometimes is devoted to solving this kind of problem. So it's good to have an idea of what's going on. Any other questions, homework? So, have no question now, come to the office hour, right? So, and ask question. If you want to get it checked, use other people in the class. Once you really code get checked, you can ask Trisha to take a look at the result and so on, right? So, use this kind of resources. All right, okay, so let's continue with this lecture then. So this lecture, so if you look at this type of coding, right? Basically, when we solve the constraint optimization, we're not actually solving a V and theta space. Because, right, even homework shows without optimization, without optimizing anything, solving the question is already hard. So when we're trying to optimize things, we mostly solve it just in the P space. We'll just say, as the demand satisfied and this kind of thing, right? We won't a lot of times touch the V and theta space when we're optimizing. Okay. Right? But so to continue with our thing from before, right? So remember, we had an equality constraint. An equality constraint is some form of ax1 plus bx2 equals to L, right? So this is our equality constraint. In our convention, it's very important to write the equality constraint in a certain way. Okay. We need to write it as L minus ax1 minus bx2. This is a convention adopted in power systems. And in power engineering, is always the right-hand side is always the constant minus a variable. Okay, it's always this. It's always written this way. So it's not L equals to F plus lambda ax1 minus b plus x2 minus L. So it's not this way. It's also not. You need the L, so it's definitely not. Right? So it's not these two, right? So the correct form is to have the L subtract the other things. This is L subtract the other things. And this is actually just a sign convention, but in power system, this is the important sign convention. Okay, this is the important sign convention. Right, so this is important sign convention. And the reason is the following, okay? The reason is the following. So let's go back to our old example and look at this too. Right, so these two are the two equality constraints, right? These are the two constraints on basically the gradient of the cost function. So we have 0.5x1 subtract lambda equals 0, 2x2 subtract lambda equals 0. This together actually implies this, right? Even without knowing what the value for lambda is. Right? This without knowing the value for lambda, this has this kind of implication. So why is this the case? Can we explain this intuitively? Why is it at optimality we need 0.5x1 equals 2x2? If this is optimization we're solving. So this basically. Why is this the case? Does this make sense? Would you expect this to happen? Right, so let's say, I claim at optimality, basically 0.5x1 equals 2x2. And this is actually the condition of things being optimal, right? And we're saying, basically, you can view this as optimality condition, saying that the partial derivatives, should be equal, right? The partial derivatives are equal. Then as we need to search for x1, x2 that satisfy the sum of them is 5. But why should this happen? Why does this make sense? Why should this make sense? And why must this partial derivatives be equal to each other at this point? Okay, so it's important to think of this, right? So we can interpret this as basically the increase, the marginal in cost. Okay, we can interpret this as being the marginal increase in cost by changing x1. And this is similar, this is a marginal increase in cost by changing x2. Basically, this equality constraint, right? So this lambda is telling us those two marginal cost needs to be equal to each other. Okay? This lambda is basically saying at optimality, the marginal cost should be equal to each other. So let's see why that is the case. Let's see why that is the case. Okay? So if you look at basically economic dispatch, right? You look at economic dispatch. So this is just a sort of more writing it out using more variables, so it doesn't say much here. But let's look at the incremental cost. Okay. If you look at the incremental cost curves, right? We're saying that at optimality, the two cost curves are the same. Right? We're basically saying that at optimal, we have equals to this two. Right? This comes from the fact that both of them equal to lambda. Right? So by introducing this lambda, we're saying they have to be the same. So why is this a case? Why is this a case? Why must they be the same? Okay, so let's think about this. So we're basically saying this, you can think of, there's some value of lambda, and there's some value of lambda, and this value of lambda basically controls when they're equal to each other. So they're supplying a load, right? So we can think of this as a load. So I need some load here, have some x1, have some x2 entering into this. So I have L subtract x1, subtract x2 equals to 0. Okay, I have this kind of situation. So I can ask if L increases, does lambda go up or down? If I increase L, does my Lagrangian multiplier go up or go down, the value of lambda? I said my old load was 5, now I increase this load to 5.1. Should the lambda go up or go down? If I increase a load. All right, so intuitively, should it go up? Do we have a feeling on this? So should lambda go up? Should lambda go down? What should lambda do if I increase L? Any guesses? So I have more load. So why would it go down, right? So look at this, right? So lambda here is the level of the marginal cost, right? Is a marginal cost. So when we have more load, should the marginal cost increase or decrease? As if I need to serve more load, does it get more expensive or less expensive to serve more load? Right, so lambda is this horizontal line, right? So we're saying at optimality, basically lambda says that the marginal cost has to equal to each other. So then if I increase the load, if I increase L, is it more expensive or less expensive to supply this load? If we're consuming more power, does the price go up or down?
Price would go up, right?
Right, price has to go up, right? So the lambda will increase, and lambda goes up, right? Because I'm basically shifting, right? So for increasing L, basically here, this is L increases, lambda also increases. Right? L increases, lambda increases. Right? So these both of them increase together. So if L decrease, lambda goes down. Right? Lambda goes down. Right? So this, because if the load decreases, then the price go down, right? This sort of the marginal cost is less compared to a higher load. Okay, so this basically lambda now has this kind of interpretation, right? This lambda basically couples the marginal cost together. Lambda couples the marginal cost together. So our interpretation is the fact that lambda now changes as L changes, right? Lambda changes as L changes, as the amount of load in the system changes. So you can look at the physical interpretation, right? So our physical interpretation of the marginal cost is sort of quite intuitive. Basically says that if the changing x is small, then the changing cost is roughly the derivative times the changing x. So we're going to think of this as the marginal cost or the price. Okay. Right, so the marginal cost has the interpretation of if I increase x by, let's say, 1 unit, how much does the cost change? Okay, so this is our interpretation of it. Okay. All right. So any questions up to here? Okay, right. So the partial derivatives basically the cost of generating, right, 1 more unit. Okay. Right. So let's then view that physical interpretation. The physical interpretation becomes dc1 dx1. And this is cost of 1 more megawatt from unit 1. dc2 dx2 as the cost of 1 more megawatt from unit 2. Okay, right? So suppose I have dc1 and dx1 larger than dc2. So these are ordinary derivatives. Okay, suppose this happens. Okay, suppose this happens. Can I find a better operating point? So if I say, at an operating point at some solution, the partial derivative, the derivative of C1 respect to X1 is larger than C2 respect to X2, can I find a better solution? Right, so if I say I'm serving some load, at this point of serving the load, I find that the marginal costs are not equal from the two generators. Right? Let's say the marginal cost is not equal. So if they're not equal from these two generators, can I, do I need to, is there an adjustment I can find to lower the total cost of the system?
You can shift more load to the cheaper generator.
Right, yeah, so you can shift more load to the cheaper generator, right? So what you do is you decrease output from unit 1. You increase output from unit 2, right? So this, what happens is the load is balanced because I increase one and decrease the other. However, my total cost decreases, right? Okay. This says, marginal cost is the same. So it's more expensive to use unit 1 than unit 2. So what I should do is, I should use less. I should use less from unit 1 and use more from unit 2. And because the marginal cost is in such a way, so in total, I decrease the total cost. Okay. Any question about this? Right, so this is sort of the economic interpretation of why the marginal cost has to be equal to each other. So similarly, basically, this is if this situation happens, I can still adjust the output from the two units, from two generators, and I can decrease the cost. Okay, this also here I can decrease the cost here, right? So if the marginal costs are not equal, right, I can always change. Right? I can always change the output such that I can reduce the overall cost. Okay? Right? I can always do that. So if you look at the physical interpretation as then at optimality, this must happen. Okay? This must happen. Because if this doesn't happen, I can find a cheaper solution. Okay? So the only time the solution is optimal is when those two happens together, when they're equal to each other. Okay? So this lambda now has an interpretation of the marginal cost. The lambda here is the marginal cost of supplying one more unit of load, right? Because this says if the marginal cost from the two generators are balanced, then this is when the problem is optimal. Okay? This is when the problem is optimal. So any questions about this? Right, so that's why in the lambda, you see lambda being called the marginal cost or the marginal price, or this is actually called the marginal price. Should be the cost, but this is often called the price in the literature. This is the marginal price. This means that if I increase the load by 1 unit, I should pay at the price of lambda. Okay, this is the economic interpretation of it, right? And so this is two ways to understand the lambda. Lambda from before is a way to encode the fact that two vectors are parallel to each other. Here, another interpretation of lambda is to encode the condition at optimality, the marginal cost of generation from all generators should be equal to each other. Okay, so both are interpretations and they're equally useful in some senses. Okay. And this is actually a big result in economics. This is the big result in economics. This is actually a specialized form of the fundamental theorem of microeconomics, actually. So every field has a fundamental theorem, right? There's fundamental theorem of calculus, of algebra, of linear algebra, and so on. This is the version of the fundamental theorem of microeconomics. Basically saying there exists a price. Okay, there exists a price. And the price tells you when the system is operating optimally. Okay? And for power system, it shows up in this form. Okay, this price links basically different generation costs. Okay, any questions with this? Okay, so this is an important interpretation. We'll come back to this interpretation a little bit later. We'll come back to this interpretation, right? So, right. So if any of you ever study microeconomics, this is, you see this very early on in microeconomics, right? This is the whole reason. Actually, you can justify the existence of the stock market based on this result. Basically, there's a price, and the price captures enough of the system, right? This is the price we have. Okay, so for power system, this tells you, look, the price exists. The price basically saying that this is when all the marginal costs are balanced, because if they're imbalanced, there should be a better solution. And so we need them to be balanced this way. Okay, so we can extend this. We can extend this a little bit more to a optimization with inequality constraints. Sorry, do I want to do inequality constraints here, or do I want to do something more? Okay, so let's finish with equality constraint. Let's finish discussion with equality constraint. Okay. So remember this physical interpretation. Remember this physical interpretation. Okay. So if you look at the system, there's many generators, right? So there's a number of generators, and maybe of different type. One is, let's say, one is hydro, one is nuclear, one's gas, and so on. Okay. So they all have different cost. They have different cost function, things like this. However, there is one price, okay, lambda, right? So this calculation tells us that if we optimize the system, optimize the economic dispatch, there's only one price, right? Lambda, okay. But there's different generators have different costs. For example, hydro may be zero cost, right? Things like this. Okay? There's one price lambda. So can you think of a way to pay the generators? Right? Let's say different generator has different cost, but there's only one price. Okay, so can you think of a way to pay the generators based on this price? How do you pay people? How should you pay people? If you solve the optimization problem, you get this price, this marginal price lambda, the Lagrange multiplier that comes out of it. But then now you actually have to pay the generator, right? You have a hydro, you have a nuclear, you have a gas, right? You have to pay people money, so they generate power for us. So how do you pay? Do you pay based on their absolute cost? Do you pay based on the price? How do you pay people? Right. So I solve this optimization problem. I have one price, but let's say I have x1 star, x2 star, x3 star. These are how much they generate. Should I pay people based on the cost evaluated at these solutions? Should I use the price somehow? How should I do this? And so you get to design the electricity market. How will you pay people? Can you think of a way to use a price to pay people? Anybody have an idea? Right, so let's yeah, go ahead.
You could pay everyone the same price, lambda.
So lambda is a price, right? So lambda has dollars per megawatt. I need to, right? So I need to somehow get rid of this per megawatt. Right? So I use the same price, but how do I convert dollars per megawatt to dollar? How do you just give money, right? How do you pay people money? Right, so the way we just pay, right? So the chat is correct, right? So payment as lambda times xi star. This is how much you get paid. This is our payment scheme. We're not going to use the cost. We're not going to look at absolute cost. But the way people get paid, at least in North America, you get paid by lambda times the amount of power you generate. You get paid price by the amount of power you generate. Okay? So this is the payment to each generators. Okay? So the load pays lambda times L. As a load, we pay lambda times L. This gets divided to the generators. Okay, this gets divided to the generators. We pay generators basically lambda times xi star. Okay? This is how the payment there is calculated. Okay, this is how payment is calculated, right? So why does this make sense? Right? Why does this make sense? Well, this makes sense, right? This makes sense from the the everyday market actually works like this, right? So you can go back to the old example. Let's say you're buying Apple, right? You're never paying the whole cost of Apple, right? You have a price of $1 per apple, and you buy 5, you pay that, right? It's the price times the amount you buy. So this is also the price times the amount you generate. So our market works the following way. Our market actually works the following way. So every day, what happens is each generator, basically, they will they submit a cost curve. Okay, so generators submit cost curve, let's say CIXI. They submit this to the system operator. And the system operator solves. So a much more advanced version of this problem, but for now, let's think of this version of being the easy version. X1 to Xn, let's say, then sum of Xi equals to L. Then pays, this has a Lagrangian multiplier lambda times Xi star to generator I. Okay, this pays lambda to generator I. So this is a payment scheme. This is a very simple version of payment scheme used in the US. Okay, so every time your electricity bill comes along, part of it depends on whatever lambda was for let's say Seattle. Okay, so we pay based on this, right? So this is called the marginal cost pricing. This is called the marginal cost payment, right? Because this, when you're a generator, all you do is you actually submit a cost curve, and then the market does this clearing, computes a price, and then you get paid based on this price, right? So as a generator, do you make money this way? Right? As a generator, do you make money? Are you always guaranteed to make money? Right? As a generator, why are you happy with this, right? Are you always guaranteed to make money? Right, so if you look at the generator curve, right? So what do you get paid if you're a generator? Okay, CIXI. Let's say you have some curve like this, and you get clear at this point, right? You get clear at this point. Your payment, right? Your payment. So let's say you have some derivative, you get some marginal cost. So your payment is actually you get paid basically this much. So the red square is actually your payment. Okay, so this is lambda times xi star. So what you have is often as this is called the profit. This is called the sort of your own cost. So for your generator, you actually get to make some money. Okay, so the generator, you make basically the money that's above this curve. Okay, so we'll do this much more. For example, you can take a class we have called Power System Economics. But the basics of this economic scheme is the ability to compute this price. Then from this price, compute the payment. And this is how the market is balanced, okay, based on this payment strategy. And right, so this is basically the major work that was done to convert the market from a monopoly. So in the US, before the, say, early 2000, everything was a monopoly, right? So payment didn't matter, just minimizing cost, right? But after 2000s, most of the US now have a so-called a structured market. And the structured market, the main thing is to work out how do you pay generators. And this was the idea that people adopted. And this is the way you should pay generators. Okay, then this is how you make money, right? Right. So, any questions about this payment scheme? Okay, so this is the way you get paid. Can you think of some ways when this goes wrong? So this does go wrong, fairly often actually. Right. Can you think of some way when this, if everything is based on one price? Can you imagine sometimes when this is not so desirable? For example, if you say, if especially as a customer, you're paying, you are paying basically this price as well, times the amount of electricity you consume. So can this price be very high in the system? Right? This price can be actually very, very high because you're depending basically on the cost function. So you may have a cost function that's super steep, and it's super steep. And this happened, for example, not this year, but last year in Texas. But what happens is the demand was higher than anticipated. And so you have a higher demand than what you thought. And then some generator came along and said, okay, I'm willing to serve the demand, let's say at $10,000 per megawatt. So the normal cost in Texas is about $30 per megawatt. And then if a generator comes along and says, oh yeah, I can serve it, but I demand $10,000 per megawatt. What you actually have to do is you actually have to pay at this price. Because the generator has to submit their own curve, and the generator can ask for a very high price. So as the demand, you basically have two choices. You either pay at $10,000 per megawatt hour, for a few days, or you have to cut demand. So you can look at in Texas, basically there was some people experienced blackout because you can't pay that much, you can't pay this price. Some people just pay that this price to serve it. Okay, so this kind of price, since there is a single price and there's one expensive generator and a little bit increasing demand, can just drive the price up for everybody. So you often see sort of this kind of price spikes. You often see this kind of price spikes. And if you're a generator, you can make a lot of money from this a few spikes. So a lot of people are in the market to just trying to make money from a few days of spiking. Right? And whether this is what you want in the system or not is debatable. So for example, California caps the price at several $1,000s per megawatt hour. So saying if the price goes above the cap, we're going to cap it artificially. And then Texas said, hey, this is a market. If you say you want a free market, this is a free market. So Texas actually has no cap, can go arbitrarily high. Okay, if you can time it right, you can make arbitrary amount of money. Basically, this can spike. In Texas, this is allowed. Right? You can, if it spikes, it spikes. And it's up to the market representative to work it out. And some other system, there's a cap. There's a lot of debate on how this thing works, how this market should work. Okay? But right now, at least most of the US still adopt the sort of the pricing market. This sort of marginal pricing as a market payment strategy. Okay? So that's something to be aware of, right? If you ever read in the newspaper to say, oh, some system, the price went to, $5,000 per megawatt hour, what happened is the demand went up, and then some generator said, hey, I only generate at $5,000 per megawatt hour. And if they're cleared, then everybody in the system pays this much. Okay? So we don't have a gradual payment scheme. That's everybody, you pay the quantity times the price. Any questions about this? About the market, about this kind of pricing? So for example, some of you may work for, let's say, Goldman Sachs. Goldman Sachs actually has a division that does power trading. And you essentially trading this kind of market, right? You hopefully you can make money in this kind of volatility, right? So this is quite common. It's commonly done. And and every 1 or 2 years you see, FERC, I think Chase a couple of years ago got a $200 million penalty for gaming the market, right? For sort of artificially creating high prices. So this happens quite often. This is, a lot of trading is done to do this. Right? But so it's good to have intuitive feeling of where you can trade in the market. Where does the price come from? It comes from for this kind of pricing scheme that we adopt. Okay. Right? And you may think this is a scheme that you take advantage of, but it's actually very hard to come up with a better scheme. There's a lot of work to say when renewable comes along, do we have a better pricing scheme? It's hard to think of a better one than this one. This makes economic sense. So the good thing is this sort of makes sense in theory. And in practice, how does it make it work is sort of open research question for us. Okay. All right, so this is sort of the pricing, and this is why lambda is a very important number. A lot of times, the market, we solve economic such. Sometimes it's to compute the set point of the generators, but often you need to report lambda because this is how people get paid. Right? So you always need to report this lambda. Okay? Right. So we won't go into very much into this today, but this is just a little bit of preview into next class. Is basically we have equality constraint. You can think of this as a power balance constraint. We have inequality constraint because we have this sort of generation constraint, right? Not every bus can generate arbitrary amount of power. So we basically need to as well have a load equals generation constraint. We need to constrain upper and lower limit of generators. Right? So basically we can solve this problem through a modification of the Lagrangian multipliers. What we do is we still set up something similar to the Lagrangian. We still reflect all these constraints upstairs. I'm going to solve it in a similar way to the equality constraint problem. Okay? But we'll go into more detail next time. Okay? So let's stop here today. Next time, we'll look at more details into this inequality constraint problem. And the reminders or homework due on Wednesday. So for the homework, for the coding, if you really cannot get to work, or there's bugs, that's fine. Just comment your code. Make sure at least runs, right? Make sure at least reads the spreadsheet and gives out y-is matrix, right? Make sure at least there's an attempt to construct the Jacobian. Okay, make sure all this happens. Make sure it runs. Make sure it's commented. When that happens, you get most of the points for that homework. Okay? And so always, use your classmates, use your TA. Ask me if you have questions. Right, thanks. So if no question for this class, I'll see you on Wednesday.
Professor?
Yeah, go ahead.
I still have a question for the homework.
Yeah, go ahead.
So for this homework one, so I built the initialize the angle and the voltage at each class. That means
right.
And for the smart bus, I don't have to because already there. And for the generation, that's one, so I can use V set as the V bus.
Yes.
But the demand, but the thing I need to initialize is generation the angle and the demand angle and the demand voltage.
Yes.
And when I build the Jacobian matrix, and you said there is a formula for the Jacobian, like because the Jacobian matrix has the four part. J11, J12, J21, and J22.
Okay.
It's because the delta P over the delta V and delta P over the delta theta and delta Q over the delta V and the delta Q over the delta theta.
Yeah, so let's say it's, some Jacobian is of this form. Let's say it's of this form.
So because the J21 and the J12 are both 0, I mean the 0 matrix here. Because
So your Jacobian is smaller, right? So let's say we're doing this, we're looking at this problem. Then this is our Jacobian matrix. So it's a 3 by 3 matrix.
Yes.
So, right, so you can plug, let's say for the initial point, you plug in, theta 0, V0 into all this, into this Jacobian matrix, and you can find the sort of numerical 3 by 3 matrix.
Okay. But because we can use the derivative from the Python and just calculate the.
No. Do not use derivative from Python. Do not use derivative from Python. That doesn't go well. Calculate the derivative by hand.
Calculate the derivative by hand.
Yeah. So the equations are fairly simple, right? The power flow equations are, just some v times some sinusoid. Just do the derivative by hand.
In the book, they actually have the derivatives in there. If you look in like chapter 6.6, they have so you don't even need to take the partial derivatives. It shows you in the book in chapter like 6.6, I think it is.
Yeah, so you can either copy that or just do it by hand. It's not terribly difficult to do that by hand. But you don't want to use the automatic differentiation in some package. That doesn't go well.
So you mean the book in chapter 6.6 has the derivative function?
Yeah, there's a derivative function. The book has it. The slides may have it. If it doesn't, you can Google online. This is very common. It's very common. And it's good to also do it by hand. It's not that hard. It takes you like 20 minutes, if that, to do the derivative by hand, right? Because just derivative, you're doing partial derivatives, so as a sine becomes a cosine becomes a sine. For v, it's when the v disappears and things like this. It's not terribly hard to do.
So because I look in the textbook here, like this is the J1, J2, J3, J4, and with the sign and the epsilon k minus the epsilon n minus the theta kn. Well, I don't know what epsilon mean here.
Which page are you looking at in the textbook?
Those are the power angles that you're solving for.
Page 355.
355. Okay, so let me take a look at what those are.
335, I think it is.
335. Okay.
55.
Oh, I don't know. Maybe you have a different version. Other what?
Should be 335, right? 355 something.
Is the power flow solution under 6.6 chapter?
It's 335.
Yeah, so this is the equation 6.6.5. Is that what we're looking for? Yeah, so you have the table, right? There's a table that gives all the derivatives if you want it. And if you don't want to use this table, since this table has a lot of information, you can just do it by hand. Like, it's really doesn't take that long.
How do you mean by take by hand? Because I know the P1 and let's say the P1 equal to the V1 times V2 times the sine and the cosine constraints.
Yeah.
V1 times V until to the V.
Okay, so let's try this, right? Let's try this. So let's try this. So let's say I have P1, right? So let's say P1.
Yes.
Okay, so P1, let's say,
Sum of the.
yeah, that's fine. So I have, sum of the j from 1 to n, vi vj, gij cosine theta I minus theta j, plus bij sine theta I minus theta j, minus pi injection equals 0, right? So this is one equation I have.
Yes.
So let's take a derivative. Let's take a derivative of this, right? So let's do, okay, so let's do this. So let's say do theta I, right? So let's do theta I of this derivative. This is j equals to 1 to n, vi, vj. This doesn't change. Theta I is not a function of this. gij sine theta I minus theta j, right?
Yes.
Plus bij cosine theta I minus theta j, right? This is my d theta I.
Yes. I mean, you do the derivative of the theta I. Okay, theta I. Yes. Okay, that's
So you
right.
do this theta j is easier because there's only one term with j, right? So let's do theta k, right? So let's do theta k. So this is vi vk.
Yeah.
So I have, gij sine theta I minus theta k, right? This is the derivative of the first term. So I have minus bij cosine of theta I minus theta k.
We don't have theta k. We have theta j.
No, this theta j is a sum, right? It's summing over all the buses that connect to I.
Oh,
Right?
j.
So this is my sum. So I'm now looking at the theta I, right? So I found a Jacobian. J is internal to the sum, right? J is the index of the summation.
Oh, so k is like could be 1 to
Yeah,
12.
K is bus 2, bus 3, bus 4, and so on.
Okay.
And where J, the summation over J is internal, is the index of the sum, right?
Okay.
So you do this, and so keep going, right? So
Yes.
do V, do Vi, do Vk, do Q with respect to all this. It's not. I just look at this equation and do the derivative.
Sure.
Right? It doesn't. It's not terribly difficult to do this derivatives. You can look at the book if you want. You can just do it by hand.
So when we do the derivative, and until what point so we can say, oh, we got the solution?
I mean, the derivative is a derivative, right? There's no. You get a bunch of formula like this.
Oh, we do the iteration like so.
Oh, in iteration, just have a reasonable judgment, right? So let's say is a 0.1% mismatch, some reasonable termination. 0.1%, for example, is a very reasonable one. And do a few more iterations, you can do 0.01%, you can do 0.5%, right?
Thank you.
Other questions about homework?
Yeah, if I can actually just quickly clarify on what I was saying before this. So over here in the powerful equation, the minus pi injected. So if it's a demand bus, or in other words, if it's a PQ bus, then we take the value from the P megawatts from the column B, I believe, and we plug in the negative of that value.
Yes.
I don't know, maybe then I don't know, maybe it's because, does it not really matter because it's the power, because for example, can't a generator in fact be consuming active power if we can technically make a system?
Sure, but
so
not in this test example, not in the data you're given.
Okay,
Yeah.
And just another, I guess, quick question. For the reactive power, we don't really care. We always plug in the negative, right? Because we only have the reactive power flow equations only at the
load. Yeah. So generator, you don't have a reactive power flow. So for load, those are always demand, interpret as demand.
And so we always plug in the negative of the.
Yes. Yes.
Okay. Okay, thank you. And then also, I guess, real quick about this derivative you were taking. I don't know, maybe I wasn't really following along, and then I looked, and if you're taking the derivative of, oh, you're taking the derivative of the very top one. Okay, I thought you were taking. Okay, okay, makes sense. Yeah.
How about the inverse of the Jacobian? Can I just use the formula from the Python?
Yeah. There should be an inverse formula, right? It should be inverse of that. Yeah. Any other questions?